Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc 06B, and the topic is the continuation of solving oblique triangles. In the previous video, we learned how to solve triangles in the form of angle, side angle, 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 side, and if possible, side, side, angle. That leaves us with the cases of side angle side and side side side. We learned that the law of sines is helpful when we have a complete family, the A family, B family, C family, and a half a family. But in the case of side angle side and side side side, we do not have a complete family. So we need another law. For instance, in the first case, which was a side angle side, we have A equals 68 degrees, B equals 8, and little c is equal to 5. We do not have a complete family. The same is true with side, side, side. We have little a equals 4, little b equals 7, little c equals 9, but no complete family. So we will now develop what is called the law of cosines. We start with oblique triangle ABC with little sides ABC. And we drop a perpendicular from C down to line segment AB. We will call it H. Looking at the right-hand triangle, it is a right triangle, and therefore we can say by the Pythagorean theorem that a squared is equal to h squared plus y squared. Dividing the line segment AB into two pieces, x and y, we can then say that a squared is equal to h squared plus c minus x, quantity squared. Focusing on angle A, we can say that the sine of A equals h over b, and therefore h is equal to b sine of A. And cosine of A is equal to x over b, and therefore x is equal to b cosine of A. Continuing with our main thread, we now replace h and x, and we get a squared is equal to b sine A squared plus quantity c minus b cosine of A squared. We expand the right-hand side and get a squared is equal to b squared sine squared of A plus c squared minus 2bc cosine of A plus b squared cosine squared of A. Rearranging our terms and doing a little factoring, we get a squared is equal to c squared minus 2bc cosine A plus b squared times the quantity sine squared of A plus cosine squared of A. But we know that sine squared of A plus cosine squared of A is equal to 1, and we are left with a squared is equal to b squared plus c squared minus 2bc cosine of A. So we have the law of cosines. Like the law of sines, it is really three laws in one, depending on which angle we are working with. We have the A law, a squared equals b squared plus c squared minus 2bc cosine A, or the B law, b squared equals a squared plus c squared minus 2ac cosine B, or the C law, c squared equals a squared plus b squared minus 2ab cosine C. We will use the law for which we have the angle. Realize that the Pythagorean theorem is just a specific case of the law of cosines. When the angle is 90 degrees, that means the cosine of that angle is 0. And the 2bc cosine A, B, or C washes out, and we are simply left with the Pythagorean theorem. So to solve an SAS problem, use the following steps. We use the law of cosines for which you are given the angle. So if you're given angle A, you will use the A law. A squared equals B squared plus C squared minus 2BC cosine A. And that allows you to say that A is equal to the square root of B squared plus C squared minus 2BC cosine of A. We can input that directly into your calculator, and you get your answer right away. Now that we have a complete family, we then can switch to the law of sines. It is advisable just to use the law of cosines once in a problem. This is important. To avoid a possible issue that we'll see later, always use the law of sines to find the smallest angle remaining. So you use the law of sines with your complete family and then the smallest side remaining. That will give us two angles, and we can easily find the other by subtracting the sum of your two unknown angles from 180 degrees. And as before, verify your answers, checking that the largest angle is opposite the largest side and the smallest angle is opposite the smallest side. Since you must use the value you found to find other values, it is advisable to store it on your calculator so that you will always be using an exact value rather than a rounded one. Let's go back to our original problem, which we will call number 17, where angle A equals 68 degrees, little b equals 8, little c is equal to 5. This is a side angle side situation, and again the law of sines is of no help. It really is not necessary to draw the picture, as there will always be one triangle possible. However, we will draw the picture just so that we get a sense of what we're trying to solve. We are given angle A, so we will use the A law, and we get that A is equal to the square root of B squared, which is 64, plus C squared, which is 25, minus 2 times 8 times 5 cosine of 68 degrees. And we get to two decimal places, 7.68. We will store that value on the calculator and now use the law of sines with angle C, the smallest angle. And we get angle C is equal to the inverse sine of 5 sine of 68 degrees divided by our stored answer 7.68, and we get 37.11 degrees. And finally, we can get angle B equals 180 degrees minus 68 degrees minus 37.11 degrees to get 74.89 degrees. So our final answer is angle B equals 74.89 degrees, angle C equals 37.11 degrees, and little a is equal to 7.68. Looking at our triangle, the answer appears to be correct. The largest angle B is opposite the largest side, and the smallest angle C is opposite the smallest side. Since angle B and angle A are relatively close to each other, so are the values of little b and little a. An illustrative problem of the danger in the law of cosines is number 18. We are given that angle B equals 14.3 degrees, little a is equal to 6, and little c is equal to 25. This is clearly a side angle side problem. We make the picture and we realize that we have a very distorted triangle. It is drawn somewhat to scale. No choice in which law of cosines to use. We must use the B law as we are given angle B. So little b is equal to the square root of 6 squared, 36, plus 25 squared, 625, minus 2 times 6 times 25 times the cosine of 14.3 degrees, and we get 19.24. So now we switch to the law of sines. We go for angle C, which is equal to the inverse sine of 25 sine 14.3 degrees over 19.24, and that gives us 18.72 degrees. And now we can get angle A to be 180 degrees minus 18.72 minus 14.3 to get 146.98 degrees. So it appears that our answer is angle A is equal to 146.98 degrees, angle C equals 18.72 degrees, and little b equals 19.24. Yet, looking at our answer, it is apparent that our answer is seriously incorrect. Looking at the picture, there is no way that angle A is equal to 146.98 degrees. And the ratio of sides to angles appears to be wrong. We know that little a is the smallest side, and yet it seems to be opposite the largest angle. Something is seriously wrong. The mistake was going for angle C first rather than for angle A. When we took the inverse sine of 25 sine of 14.3 degrees over 19.4, we were taking the inverse sine of 0.321. Realize that there are two angles who have a sine of 0.321. One in the first quadrant, one in the second quadrant. The calculator determines the one in the first quadrant, but it is clear that angle C is the largest angle, and we therefore want the one in the second quadrant. The calculator does not know this. And therefore, since angle C is wrong, then angle A is wrong. So the solution is to always go for the smallest angle first. There can only be one angle in a triangle that is greater than 90 degrees. So if we go for the smallest angle, it cannot be greater than 90 degrees. So we will go for angle A first. So going for angle A first, we get angle A is equal to the inverse sine of 6 sine of 14.3 degrees over 19.24, and then we end up with 4.42 degrees. Therefore, angle C is equal to 180 degrees minus 4.42 minus 14.3, and we get angle C is equal to 161.28 degrees. So our correct angle has angle A to be 4.42 degrees, angle C equals 161.28 degrees, and little b equals 19.24. This now appears to be right. The largest angle, C, is opposite the largest side, and the smallest angle, A, is opposite the smallest side. That is why I always recommend making a picture. If the picture is drawn somewhat to scale, then your answers will make sense. Finally, let's go through the steps to solve a side-side-side problem. The only curve that your teacher could throw you is a side-side-side problem that does not exist. In a triangle where three sides are given, the sum of any two sides must be greater than the third. Assuming that's true, here are the steps. First, we can use any of the law of cosines. It is suggested, though, to avoid the problem that we saw on the last page, it is suggested that we use the law of sines to find the largest angle. So if A is the largest side, use A squared equals B squared plus c squared minus 2bc cosine A that allows you to solve for cosine A equals b squared plus c squared minus a squared all over 2bc. We're going to calculate the value of the right side of this equation using the calculator and then take the inverse cosine of that answer to find A. We now have a complete family, so we switch to the law of sines. Only use the law of cosines once in a problem. So use the law of sines with your complete family and any other half family. If you have used the law of cosines to find the largest side, the issue that cropped up before will not crop up, and you can use either side that is given. Now you have two angles, and we find the other angle by subtracting the sum of the two angles from 180 degrees. Again, we verify our answer with our normal check: largest angle opposite largest side, smallest angle opposite smallest side. And as before, since we're going to use the value you find to find other values, it is recommended that you store it on your calculator so you will always be using an exact value rather than a rounded one that you typed in. In number 19, we're given that A equals 7, B equals 9, and C is equal to 12. As before, it is not necessary to draw the picture, but it helps to give you a sense of what you're finding. The triangle exists because the sum of any two sides is greater than the third. Since C is the greatest side, we will use the C law with our law of cosines. And C is equal to the inverse cosine of a squared plus b squared minus c squared all over 2ab. So we take, using the calculator, the inverse cosine of a squared, which is 49, plus b squared, which is 81, minus c squared, which is 144, over 2 times 7 times 9. We don't have to actually do the calculations. We can take the inverse cosine of whatever that is, and we end up getting 96.38 degrees. From there, we will find angle A. And we use the law of sines and say that A is equal to the inverse sine of little a sine C over C, or the inverse sine of 7 sine of 96.38 degrees, which we stored, divided by 12 to get 35.43 degrees. And finally, angle B equals 180 minus 96.38 minus 35.43, getting 48.10 degrees. So our final answer is angle A equals 35.43 degrees, angle B equals 48.19 degrees, and angle C equals 96.38 degrees. Looking at those angles and sides, the proportions seem correct. The largest angle is opposite the largest side C, and the smallest angle is opposite the smallest side A. And since A and B are relatively close to each other, so are angles A and B. In number 20, we're given that A equals 6,000, B equals 4,000, C equals 5,000. When we draw our picture, we can save ourselves some work by realizing that we can use, instead of 6,000, 4,000, 5,000, the numbers 6, 4, 5. The triangles are not congruent, but they are similar, meaning that they will have the same angles. And it will save us from having to work with huge numbers in the calculator. You don't have to do this, but it is suggested. We draw the picture, and again, it is relatively close to an equilateral triangle, but it certainly is not. Angle A will be the largest angle because it is opposite the largest side, and therefore we will use the A law. A is equal to the inverse cosine of b squared plus c squared minus a squared over 2bc. This becomes the inverse cosine of 4 squared, which is 16, plus 5 squared, which is 25, minus a squared, which is 36, over 2 times 4 times 5. We do the calculation and take the inverse cosine of that calculation, and we get 82.82 degrees. It doesn't matter which angle we go for next. We'll go for angle B, and that becomes the inverse sine of B sine A over A, or the inverse sine of 4 sine of 82.82, which we stored, over 6, and we end up getting 41.41 degrees. And therefore, angle C is 180 degrees minus 82.82 minus 41.41 degrees to get 55.77 degrees. Our final answer is angle A equals 82.82 degrees, angle B equals 41.41 degrees, and angle C equals 55.77 degrees. Angle A is the largest and its opposite little a. Little b is the smallest opposite little b. Now that we can solve any triangle that is solvable, we now turn to finding the area of such a triangle. We start with either acute triangle ABC or obtuse triangle ABC. And if we know an angle, it is easier to use this first formula. We start out with the area is equal to 1/2 base times height. And since the sine of angle A is equal to h over b, the hypotenuse, then h is equal to b sine A. So replacing that in the formula, we get the area is equal to 1/2 the base, which is c, times the height, which is b sine A. So we can say that the area is equal to 1/2 BC sine A. Similarly, we can say that the area is equal to 1/2 AC sine B, or the area is equal to 1/2 AB sine C. So if we have a side angle side situation, we have an easy formula to calculate the area. If we have three sides, A, B, and C, we can certainly find either of the angles and use the formula we just developed. However, there is an easier formula called Heron's formula. And it says that if triangle ABC has sides, little a, b, and c, then the area of the triangle is given by the square root of s times s minus a times s minus b times s minus c, where s is the semi-perimeter of the triangle, a plus b plus c all over 2. This doesn't appear to have anything to do with trig, but it does because the formula comes from using one of the trig identities. We will not show that proof. In number 21, we're given that angle A equals 68 degrees, little b equals 8, and little c is equal to 5. We draw the picture, although it is not necessary. Since this is side angle side, we can say that the area is equal to 1/2 8 times 5 times the sine of 68 degrees, and we get 18.54. Notice that I write out the word area and do not use A so that we do not confuse it with angle A. To check, let's use Heron's formula. We first solve for little a, which is the square root of 8 squared plus 5 squared minus 2 times 8 times 5 cosine of 68 degrees, and we get 7.68. We store that answer and take the sum of 7.68 plus 8 plus 5 divided by 2, and we get 10.34 as our value of s. So the area is equal to 10.34 times 10.34 minus 7.68, which is 2.66, 10.34 minus 8, which is 2.34, and 10.34 minus 5, which is 5.34. And we get the same answer, 18.54. It is clear that the first formula is far easier. In number 22, we have angle B equals 14.3 degrees, little a equals 6, little c is equal to 25. And again, we show the very obtuse triangle to the right. Again, this is a side angle side problem, so the area is equal to 1/2 6 times 25 times the sine of 14.3 degrees, or 18.52. Again, we can use Heron's formula to check our work. B would equal the square root of 6 squared, 36, plus 25 squared, 625, minus 2 times 6 times 25 cosine of 14.3 degrees, which is 19.24, and we should store that value. The semi-perimeter is 6 plus 19.24 plus 25 divided by 2, which is 25.12. And we should store that value too. So therefore the area is equal to the square root of 25.12 times 25.12 minus 6, which is 19.12, times 25.12 minus 19.24, which is 5.88, times 25.12 minus 25, which is 0.12. And our answer is exactly the same, 18.52. Let us look at two side-side-side problems that we encountered previously. First, in number 23, we have little a equals 7, little b equals 9, and little c is equal to 12. First, calculate s, which is 7 plus 9 plus 12 divided by 2, which is 14. So our area will equal the square root of 14 times 14 minus 7, which is 7, times 14 minus 9, which is 5, times 14 minus 12, which is 2. And we get an area of 31.30. We also had a 6,000, 4,000, 5,000 triangle. We created this and eliminated the thousands and just looked at a 6, 4, 5 triangle. And therefore, using Heron's formula, S is equal to 6 plus 4 plus 5 divided by 2, or 7.5. So the area of that triangle would be the square root of 7.5 times 7.5 minus 6, which is 1.5, times 7.5 minus 4, which is 3.5, times 7.4 minus 5, which is 2.5. But we must multiply that answer by 1,000 because we divided by 1,000 in creating our triangle, and we get our area is equal to 9,921.57. Next, we have two problems involving side-side angle. As you recall, this caused us to decide first whether triangles actually exist, and there was the possibility of two triangles. In number 25, we have angle A equals 31 degrees, little a equals 22, and little b is equal to 9. We do not have the correct information to use either the SAS area formula or the Heron's formula. So we will try to find angle B. And we get angle B is equal to the inverse sine of B sine A over A, or the inverse sine of 9 sine of 31 degrees over 22. And we get 12.16 degrees. From that point, we can get angle C. which is 180 degrees minus 31 degrees minus 12.16 degrees, or 136.84 degrees. So now we have enough information to use the area formula with SAS. So the area will equal 1/2 times 22 times 9 times the sine of 136.84, and we get 67.72. Number 26 we did previously as well. Angle A equals 25 degrees, little a equals 11, and little b is equal to 14. The picture is shown, and we see that there are two possible triangles here. So we need to find the area of both. For the big triangle in blue, we start getting the angle B, which is the inverse sine of B sine A over A, or the inverse sine of 14 sine of 25 degrees over 11, getting 32.54 degrees. From there, we can get angle C to be 180 degrees minus 25 degrees minus 32.54 degrees, or 122.46 degrees. So now we can use the SAS area formula and find that the area of the big triangle in blue is 1/2 times 11 times 14 times the sine of 122.46 degrees, or 64.97. To solve for the little triangle in red, we get angle B prime is 180 degrees minus 32.54 degrees, or 147.46 degrees. We can then get angle C to be 180 degrees minus 25 degrees minus 147.46 degrees, or the very small 7.54 degrees. So the area of the little triangle will be 1/2 times 11 times 14 times the sine of 7.54 degrees, or 10.10. In our Chapter 3 study of right-angled trig, we examined real-life applications. We continue that study to oblique triangles, but are no longer confined to triangles with right angles. This allows us to have more realistic problems. So as before, we draw a picture to describe the situation, and then label the picture with variables, being sure to use those variables in your solution. We need to identify whether the resulting triangle is an ASA, AAS, SSA situation requiring the law of sines, or an SAS or SSS requiring the law of cosines. Sometimes you have to use these laws first and then use right-angle trig. If an area is required, we need to decide whether the SAS formula, area equals 1/2 BC sine A, is needed, or Heron's formula where SSA is required. Always remember to answer the questions asked, and always remember to supply proper units to the answers. I suggest that you circle the answers. In number 27, we are told that a tree leans 7 degrees to the vertical. At a point 40 feet from the tree, on the side closest to the lean, the angle of elevation to the top of the tree is 24 degrees, and we would like to find the height of the tree. We draw the picture showing the tree leaning, labeled by T. If it leans 7 degrees to the vertical, the angle of the tree is 83 degrees, and the angle of elevation to the top of the tree is 24 degrees from that point 40 feet away. That makes the remaining angle 73 degrees. This is an angle-angle side situation, allowing us to write T over sine of 24 degrees is equal to 40 over the sine of 73 degrees. And we can solve for T, getting 40 sine 24 degrees over sine 73 degrees, and the height of the tree is 17 0.01 feet. In 28, we are told that we have two markers, A and B, on the same side of a river that are 58 feet apart. We have a third marker located across the river at some point C. A surveyor determines that angle CAB equals 68 degrees and angle ABC is equal to 52 degrees. We need to know two things: the distance between point A and point C, and also the distance across the river. The picture for 28 is not given, but it can easily be drawn if you take it slowly. We have a riverbank and 2 points A and B 58 feet apart. We have the other side of the river where there is a point C, and now we just fill in the angles. Or angle CAB equals 68 degrees, angle ABC is equal to 52 degrees, and therefore angle C is equal to 60 degrees. We want to find the distance between points A and C, which is little b, and we also like to find the distance across the river, which is the perpendicular distance, and we will call that D. We can put that line of D anywhere we want to. I choose to put it on the far left. To solve, we use an angle-side situation and set up a law of sines with b over sine 52 degrees equals 58 sine over sine of 60 degrees. And therefore, little b equals 58 sine of 52 degrees over sine 60 degrees, which is 52.78 feet. To solve for d, we're going to use right angle trig, and we can set up a statement that says that the cosine of 22 degrees is the adjacent d over the 52.78 that we just found. Again, it's a good idea to store that value so you don't lose any accuracy. And d is equal to 52.78 times the cosine of 22 degrees. You can write 52.78, but realize that there are more decimal places to the right of it. And we end up getting an answer to two decimal places that the distance across the river is 48.93 feet. In number 29, we're told that a hot air balloon is hovering over Valley Forge. Person A views the balloon at an angle of elevation of 25 degrees, while person B views the balloon at an angle of elevation of 40 degrees. If A and B are 4,000 feet apart, we want to find the height of the balloon. In this case, we are shown the picture, and it's clear that A and B are on either side of the balloon. When we only had right angle trig as our weapons, we had to do this in several steps. We let x represent the distance from A to H, and we could say that tangent 25 degrees is equal to H over x, while tangent 40 degrees is equal to H over 4,000 minus x. Cross multiplying, we get statements that are both equal to h, and therefore x tangent 25 degrees is equal to 4,000 minus x quantity tangent 40 degrees. Bringing all the x's to one side and factoring, we get x quantity tangent 25 degrees plus tangent 40 degrees is equal to 4,000 tangent 40 degrees. And therefore x is equal to 4,000 tangent 40 degrees over tangent 25 degrees plus tangent 40 degrees. There really is no need to calculate that because we know that h is equal to this value of x times 25 degrees. So doing it all in one fell swoop on the calculator, h is equal to 4,000 tangent 40 degrees, tangent 25 degrees, all over tangent 25 degrees plus tangent 40 degrees, getting 1,198.95 feet. Using the law of sines, this is much easier. We still want to find h, and h is not part of the oblique triangle. However, we know that in triangle ABC, we can get angle C to be 115 degrees. And therefore, we can use the law of sines with angle, angle, side to say that A is 4,000 sine 25 degrees over sine of 115 degrees, getting 1,865.23 feet. And therefore, H is equal to that value times sine of 40, and we end up getting the same exact answer of 1,198.95 feet. In number 30, we'd like to do the same problem using the same angles and distances, but now we're assuming the people are on the same side of the balloon as seen in the accompanying picture. So we see that angle A is 25 degrees and angle B is 40 degrees, making the obtuse angle 140 degrees. And in triangle ABC, that makes angle C equal to 15 degrees. We are not going to show the right angle trig method. We're just going to use the law of sines. And we can say, using the law of sines, that A is equal to 4,000 sine of 25 degrees over sine of 15 degrees, which is equal to 6,531.49 feet. We still want h, and therefore, looking at the small triangle, we could say that the sine of 40 degrees is equal to h over a, and therefore h is equal to a sine 40, which is 6,531.49, which hopefully you stored, times the sine of 40 degrees, getting 4,198.36 feet. Number 31 reads, two tornado spotters are on a road running east-west and are 25 miles apart. The west man spots a tornado at bearing north 37 degrees east, while the east man spots the same tornado on a bearing of north 56 degrees west. How far is the tornado from each man, and how far is the tornado from the road? We draw the picture with AB along the horizontal, a distance of 25. Remember that when we are giving bearings, they are measured from the nearest north-south line. So the west man, which is A, spots the tornado at bearing north 37 degrees east, making angle A 53 degrees. And the east man, B, spots the same tornado on a bearing of north 56 degrees west, making angle B 34 degrees. We want to find little a, which is the distance from B. We would like to find little b, which is the distance from A. And we'd also like to find, we will call it D, which is the distance from the tornado to the road. Angle C is 93 degrees. So we have all three angles and a side, and we can use the law of sines. So to get the distance from B, we will use the law of sines with angle A and angle C, and we get A is equal to 25 sine of 53 degrees over the sine of 93 degrees, which is 19.99 miles. The distance from A uses little b, and therefore we're using the law of sines with the B family and the C family, and we get B is equal to 25 sine of 34 degrees over sine of 93 degrees, and we get little b, which is equal to 14 miles exactly. And therefore the distance from the road, we could use either of the right triangles, and we get 19.99 sine of 34 degrees, which is equal to 11.18 miles. In number 32, we are told that a small ship travels from a lighthouse whose light only shines east, traveling on a bearing of north 70 degrees east, a distance of 8 miles. It then makes a turn to the right and travels for 5 miles and finds itself directly in the beam of the lighthouse's light. We'd like to know how far the lighthouse is from the ship. This problem is a little bit more complicated. We will start at A, where the lighthouse is, and we will travel along north 70 degrees east, which means angle A is 20 degrees. And we travel for 8 miles to point C. At that point, we're going to make a right turn. And we're going to go down to the horizontal line where the light is shining, a distance of 5 miles. However, we can see by the picture that there are two possibilities. We could either make a very sharp turn, getting down to B prime, or not as sharp a turn and get to B. This is the classic side-side angle situation, and we're going to need to solve both triangles. As we've done with side-side angle situations, we will solve the big triangle ABC first. Angle B is equal to the inverse sine of B sine A over A, or the inverse sine of 8 sine of 20 degrees over 5, or 33.18 degrees. Therefore, big angle C is equal to 180 degrees minus 20 degrees minus 33.18 degrees to get 126.82 degrees. So now we can get big C, which is A sine C over sine A, or 5 sine 126.82 degrees over the sine of 20 degrees, which is 11.70 miles. So one possibility is that the ship is 11.70 miles from the lighthouse. Now we go for triangle AB prime C. Angle B prime will equal 180 degrees minus 33.18 degrees, which is 146.82 degrees. Therefore, angle C in the little triangle is 180 degrees minus 20 degrees minus 146.82, which is a very tiny 13.18 degrees. So now we get little c is equal to A sine C over sine A, or 5 sine of 13.18 degrees over the sine of 20 degrees, which is 3.33 miles. So it is possible that the ship is 3.33 miles from the lighthouse. So the bottom line for this question is we really don't know how far the ship is from the lighthouse, but we do know that there are two possible answers, 11.70 miles or 3.33 miles. Number 33 reads, on a regulation baseball field, the four bases form a square whose sides are 90 feet long. The center of the pitching mound is 60.6 feet from home plate. How far is the mound from first base? The picture is clear. We see the pitching mound and the plate 60.6 feet away. And since we have a square on the baselines, then the angle from the pitching mound to home plate to first base must be 45 degrees. And of course, the side of the baseline is 90. Therefore, we have a side angle side situation, and therefore the distance opposite the 45 degrees will be the square root of 60.6 squared plus 90 squared minus 2 times 60.6 times 90 times cosine of 45 degrees, and we get the distance is 63.71 feet. 34 reads, to determine the distance across a lake AB, a surveyor goes to point C where he can measure the distance from C to A and from C to B, as well as the distance angle ACB. If AC is 314 feet and BC is equal to 865 feet, and angle ACB is 68 degrees 4 minutes, find the distance AB across the lake. We draw the picture carefully. Note that we cannot choose point C indiscriminately. C must be at a location where we can walk from A to C and from B to C without going over water. If either line segment AC or BC goes over water, then we are losing the point of what we are trying to do, to measure a distance across water. This is a side angle side situation, and therefore we use our law of cosines and get d is equal to the square root of 314 squared plus 865 squared minus 2 times 314 times 865 cosine of 68 degrees 4 minutes, and we get d is equal to 802.44 feet. 35 reads, the Bermuda Triangle is an area where ships reportedly disappear with regularity. It is a triangular area between Miami, Bermuda, and San Juan, Puerto Rico. If Bermuda is 1,035 miles from Miami on heading 64.09 degrees, and San Juan is 1,033 miles from Miami on heading 119.27 degrees, find the perimeter and area of the Bermuda Triangle, ignoring the curvature of the Earth. Shown is a map of all three locations. Remember that headings are drawn from the north in a clockwise direction. So a heading of 64 degrees 0.09 will go from Florida to Bermuda and will be the angle shown. The heading 119.27 degrees means that the angle from the south is 60.63 degrees. And that makes the angle of the Bermuda Triangle 180 minus 64.09 minus 60.63, which is 55.28 degrees. We also see the distances, and we want the perimeter of that triangle and the area. We have a side angle side situation, which means to find the area, we can use the formula that is 1/2 the product of the two sides times the sine of the included angle. However, since we want the perimeter, we need to get the third side. So we will do that using the law of cosines, and we get that the third side, which is the distance from Bermuda to Puerto Rico, is the square root of 1,035 squared plus 1,033 squared minus 2 times 1,035 times 1,033 cosine of 55.28 degrees, which is 959.38 miles. And therefore, if we're going to find the area, we would need to calculate S, which is the sum of the three sides divided by 2, which is 1513.69. And therefore the perimeter is double that, which is 3,027.38 miles. And now we might as well use Heron's formula, and we get the area is equal to the square root of 1513.69 times 478.69 times 480.69 times 665.31. All the values that we received above should have been stored, so we get exact answers, and the area is 439,393.45 square miles. Number 36 reads, circular tracts of land with diameters 900 meters, 700 meters, and 600 meters are tangent to each other externally. There are houses directly in the center of each circle, and we'd like to find the angles of the triangle connecting the houses and the area of that triangle. The picture is straightforward. We show our three circles with radii 450, 350, and 300. And that will make our sides 800, 650, and 750. We will label our sides to be A equals 800, B equals 750, and C equals 650. And therefore, angle A is equal to, by the law of cosines, the inverse cosine of 750 squared plus 650 squared minus 800 squared over 2 times 750 times 650, and that gives us 69.28 degrees. We then go for the smallest side, which will be the 650 or angle C, and we get the inverse sine of 650 sine of 69.28 over 800, and we get 49.46 degrees. And therefore, angle B is 180 degrees minus the 69.28 minus the 49.46, which is 61.26 degrees. So those are our three angles. We will use Heron's formula to get the area. S is equal to 800 plus 750 plus 650 all divided by 2, which is 1100. So the area is the square root of 1100 times 300 times 350 times 450, which is 227,980.26 square meters. Back in chapter 3, we learned about triangulation, which was the process of determining the location of a point by forming triangles to the point from known points. Here are two problems from chapter 3, which we can now do in a much faster and easier way now that we are armed with the law of sines and the law of cosines. In number 37, we have the fact that police want to determine the position of a suspected drug dealer. They will use triangulation with two cell towers 10 miles apart on an east-west line. Using his cell phone signal, they determine that his location is on heading 12 degrees from cell tower A and heading 305 degrees from cell tower B. We'd like to know how far the drug dealer is from tower A. We originally drew this picture in this way. We drew the east-west line from A to B, a distance of 10. And from A, the heading was 12 degrees, making the north angle 12 degrees. From B, the heading was 305 degrees, making the north angle 55 degrees. We dropped the perpendicular from the phone down to line segment AB, and we use both right triangles to calculate our answer. Using oblique triangles, we now can find angle C to be 180 degrees minus 78 minus 35, and that gives us 67 degrees. We can use the law of sines. B over sine B is equal to C over sine C. And we want to find little b, the distance from the cell tower A to the phone. And little b is equal to C sine B over sine C, or 10 sine 35 degrees divided by sine 67, and we get b equal to be 6.23 miles. 38 is more complicated. Scott is hiking alone and gets hurt. Luckily, he has a GPS device that is constantly putting out a signal. Ranger Station B is 20 miles away from Ranger Station A and on heading 143 degrees. From Station A, Scott's GPS device is located along heading 164 degrees, and from Station B, the GPS is located along heading 277 degrees. How close is the nearest ranger station to Scott? Creating the picture involved careful interpretation of angles. We knew that station B is on heading 143 from station A, making the top angle 53 degrees. We knew that the GPS was along heading 164 degrees from A, making the bottom angle 16 degrees. And that allowed us to say that the angle A was 21 degrees. From station B, the GPS was located along 277 degrees, and therefore the lower angle from B is 7 degrees. We also knew that because of right triangles, the top angle from B is 37 degrees, making angle B to be 46 degrees. We then drew a perpendicular from the GPS down to line segment AB, and that was the source of our right triangles, and we were able to do the problem. Now, knowing two angles allows us to find the third angle, and angle C will be 180 degrees minus 21 degrees minus 46 degrees, which is 113. We would like to find the nearest ranger station to Scott, and that distance, which we found, was S because it is opposite the smallest angle of 21 degrees. We will call this A, and therefore A over sine A equals C over sine C, and A is equal to C sine A over sine C, or 20 sine 21 degrees over sine 113 degrees, and that gives us the distance A, which is equal to 7.79 miles. That completes our section in precalculus on trig. We will revisit trig in chapter 11 when we look at vector functions and imaginary numbers. They have great uses in those areas.